Students and parents, my name is Glenn Arnold. I am a chemistry teacher at the LNN STEM Academy, and I'd like to welcome you to today's lesson on concentrations in acids. The appropriate packet to do some work on this you can find in the student section at the KCS website. So if you want to pause real quick and jump over there and grab that stuff, that would be great. But really, you can just take some notes from here and then work that later. So to start out, I just want to refresh your memory with some stuff from middle school. So first off, we're going to be talking about solutions today, and solutions are an example of a mixture. Remember that mixtures are where you've got two or more things that are combined, but they're not chemically reacted together. In other words, they haven't formed a brand new substance. There's no chemical reaction, a real chemical equation that's going on there. Solutions are a special variety of mixtures. In fact, generally speaking, we're going to call them a homogeneous mixture. They're a mixture in which the particles of the one substance that's dissolved are so small that they're completely dissolved, and they're pretty much always going to stay there. So my favorite example of that is a glass of iced tea, where the tea particles are pretty much completely dissolved in the water. You shouldn't have any tea leaves down at the bottom. Nobody likes that in their glass of tea. And so that is what a solution is. The two things that really matter for us here when we're talking about solutions are the solute and the solvent. Okay, and so if you look at this little diagram here that we have, if we're pouring some sugar or some salt, kind of hard to tell what it is in this picture, into a glass of water, the thing that we're putting in is the solute. Okay, so the solute is the substance that is going to be dissolved. The water is the solvent, the thing that is doing the dissolving. Now, sometimes if we were talking about some more esoteric cases, it would be a little harder to figure out what that is. So like if we were talking about, hey, we've got this metal dissolved into this metal to make an alloy, that it gets a little bit harder sometimes to figure out what the solute and the solvent is. Most of the time for us in chemistry, it's pretty easy. The solid dissolved in the liquid, the solid is the solute, the solvent is the liquid. Again, it is definitely not always that way. I should say right here that water is what we call the universal solvent. That doesn't mean that it dissolves all things, but it's going to dissolve a lot of things. And in fact, obviously, it's going to be really necessary for life, and so it's really important for us, and so it sort of gets the terminology. So how do we know if something is necessarily going to be dissolved? Well, solubility, whether or not something is going to dissolve, is going to be determined by polarity. That term solubility we're not really going to get into today, but that basically means does something dissolve into something else? And that's pretty much entirely dissolved by polarity. The rule of thumb, sort of the easy catchphrase that we use for that is like dissolves like. And what that means is that polar substances, polar solvents dissolve polar solutes or ionic solutes. So for instance, water is polar, table salt, NaCl, is an ionic compound, and so therefore water does a pretty good job of dissolving salt. And that's why, like, if you went to the ocean, there are a whole bunch of things that are dissolved into that water, a lot of them being ionic compounds or ions of metals and things like that. They're going to dissolve really readily into a polar substance like water. Non-polar substances will dissolve other non-polar things. So maybe, for instance, at some point, someone in your family was out working on the car and they got some grease on their hands and it wasn't coming off. And so they used a special kind of soap, or maybe they put like some WD-40 on their hands and washed that off real quick. That's because non-polar things dissolve non-polar things. Things that are non-polar are going to help to dissolve other non-polar things like grease. So a good example of this would be our diagram over here, or our picture over here on the side, where we've got oil sitting on top of water. Those two things don't mix. They're called immiscible because this top layer here is oil and it is non-polar, and the bottom layer down here on the bottom is water, which is polar. And so those two things don't dissolve very well into each other. They are said to be immiscible. Okay, so on to the heart of today's lesson. The heart of today's lesson is on concentration. What really concerns us a lot as chemists is how much of that solute is dissolved into the solvent. You've probably heard the line at some point that dosage is what really matters. So for instance, if someone has accidentally swallowed or inhaled something dangerous to them, the real question would be how much of that substance have they imbibed? How much of that substance did they get inside of themselves? If they only got a really tiny amount, that might not be as dangerous as if they got a really massive amount. Dosage is what matters. Dosage essentially is another way of us saying concentration, and so that is how much of the solute is dissolved into the solvent. So if we look at these two glasses of tea here, we can see that one of them is a lot darker than the other one. And so what we could say here is that this one is pretty concentrated, okay? And that the other one we would say is pretty dilute. Now for me, I want to drink this concentrated tea. I definitely do not want to drink a weak or dilute tea. And weak is another word sometimes that we would use for that. Now those are both qualitative descriptions. Now of course qualitative descriptions are okay in science, but a lot of times we want something a lot more concrete. We want some numbers associated with that. We want quantitative values. So a lot of times out in the world you would see concentration measurements like ppm, which is parts per million. That would mean in a million molecules. If there was one molecule of that substance, then that would be 1 part per million or parts per billion. We can also have percent. So like if you pulled off some, say, hydrogen peroxide in the store, it was probably a 3% solution, and that's usually a 3% mass to volume solution. Or it could be a percent mass solution, depending on what the two substances were. Now for chemists, what we really care about for concentration is we care about something called molarity. You've already learned about moles. Obviously moles are sort of the central thing for chemistry. And so molarity is how many moles of the solute are dissolved in the total number of liters of the solution. Now, obviously what this means is that we're going to have to convert things into moles, because obviously we don't measure moles in the lab. What we measure most of the time in the lab are grams. You've already learned how to convert grams into moles at this point, and so we would need to do that. And then we would divide that by the liters of solution. Now you'll note that that says the liters of solution, not the liters of solute. 99% of the time we can use those two things interchangeably, okay? So I wouldn't stress about that. Once in a while you won't. Most of the time if you're working a molarity problem, it would say assume that the final volume is unchanged. That just means that whatever liters of the solvent you were given, you can use as the liters of solution. So let's work a problem. So what is the molarity of a solution that contains 24.5 grams of sodium hydroxide dissolved in 500 milliliters of water? Okay, so this is this 24.5 grams of sodium hydroxide. Sodium hydroxide, by the way, and of course you already know this because you've done formulas already, but sodium hydroxide is NaOH, 1 sodium, 1 hydrogen, 1 oxygen. That is, in this case, this is our solute. That is the stuff that is being dissolved. And our solvent is going to be water. Chances are if you've got water in any type of problem, it is probably your solvent. Is it always? Not necessarily, but generally speaking, it's going to be. Okay, and so real quick, let's just write down what our formula is, just to make sure that we know what that is, and we don't necessarily have to go back to the last slide. Molarity, which is capital M, is moles per liter. Now, of course, that's moles of solute, liters of solution, but we can abbreviate that out a little bit. Now, the problem here is that I don't have moles of my solute. I have grams. So that's okay, though. We already know from previous adventures in chemistry how to convert grams into moles. So the way that we would do that is that we take the molar mass of sodium hydroxide, and that molar mass of sodium hydroxide, we could calculate that out. I'm not going to walk through that whole calculation now, but it is 40.0 grams of sodium hydroxide is equal to 1 mole of sodium hydroxide. You can refer to some previous videos or lessons on how to determine that molar mass. Basically, you're taking those numbers off the periodic table, right? The atomic weights. And so that's going to give us 40 grams of sodium hydroxide on the bottom of our conversion factor here, 1 mole on the top. And when we calculate that out, we are going to get 0.6125 moles of sodium hydroxide. Okay, so pretty straightforward. We're then going to take that back over here to our equation. Okay, and so we've got 0.61, sorry guys, that decimal didn't turn out too good, 6125 moles of sodium hydroxide, and then we need to put that over the liters of solution. Now this isn't in liters, it's in milliliters. We know how to convert that though, 1, 2, 3 steps over, and that's going to give us 0.500 liters of the solution on the bottom. We're going to punch that into our calculator, 0.6125 divided by 0.5, and that is going to give us a molarity of 1.23 molar. Okay, now you don't have to write it as 1.23 with a capital M. That's how I would pronounce that, 1.23 molar. You could also write that out as 1.23 moles per liter. And depending on the textbook or depending on the problems you're working, those two things are interchangeable. You could definitely use those at any point. Okay, now is that the only way that we would see a molarity problem? No, actually probably a pretty common way is that you don't have a solid, but maybe you already have a concentrated solution. So maybe you looked in the lab and you had a 6 molar solution of HCl, and your teacher asked you to make a 0.1 molar solution of HCl. And so you don't have any solid to measure in and use that molarity equation from before. So instead we would use something called the dilution equation. The dilution equation, for those of you that have done your gas laws already, you'll notice that it looks a lot like Boyle's law. And essentially what it means is your initial molarity, your initial volume is equal to the final molarity times the final volume. Okay, usually what we would call the initial one is we would call that the stock molarity. We would call it the stock because if I went back into the stock room and I pulled out my 6 molar solution of HCl, that would be the stock solution. Okay, and then in this case, in the problem that I'm sort of throwing out here, the molarity that I'm looking for would be M2. And then however much of it I wanted, let's say that I wanted 250 milliliters of it, that would be my second volume. And so then typically what I'm solving for is V1. Okay, in other words, how much of this guy do I need to go into the cabinet, pour out into a graduated cylinder and measure out so that I could get my final volume of my 250 milliliters. That's how the dilution equation worked. Again, if you've done gas laws and done any Boyle's law stuff, it works exactly the same way. You should have 3 numbers available to you and 1 number is a variable, and then you just solve for that last variable. So let's work one of those. So you need to create 500 milliliters of a 1.2 molar solution of hydrochloric acid. In the acid cabinet, okay, the stock room, is a bottle of 12.0 molar hydrochloric acid. How much of the stock hydrochloric acid do you need to measure out to make your solution? Okay, so we're going to use the dilution equation. So I think anytime you're working any sort of math, if you've got time, and you do most of the time, write the equation out. And then I'm just going to go back up into the original here and sort of note which of the variables each of these things are. And then I can come back in and plug them in. Or you could write them all out individually. And I think that also is a pretty good way to go. So my stock concentration is 12 molar. Okay. My final concentration that I'm looking for, that I'm solving for, so M2 is 1.2 molar. You'll notice that those are related. It's almost like I was trying to make the math easy. And then we go up here and our final volume, or our volume of the second concentration that we're looking for, is 500 milliliters. Now here's the thing. It doesn't really matter how you set all of this stuff up as long as you're consistent. Since this volume goes with this concentration, they both have to be on the same side of the equation when I set them up. Okay, so just make sure you're doing that. And then what we're solving for then is V1. That is our unknown in this particular case. So we're going to come over here, we're going to plug everything in. My stock volume was 12 molar. Okay, I'm looking for V1. If you wanted to, algebraically, you could just plug in an x there and solve for x. That's totally legit also. 1.2 molar times 500 milliliters. Okay, we're solving for V1. I want to get it by itself, so algebraically, we're going to divide both sides by 12 molar. Okay, and then when we plug all of that in, okay, make sure you cancel that stuff out. And we solve for V1, then V1 is going to come out to be 50 milliliters. Now what you may have noticed here is that I didn't convert my milliliters into liters here. You absolutely could have. I could have plugged in 0.5 liters here, and then I would have got 0.050 liters. That would have been totally okay too. But most of the time in the lab, you're not pouring out whole liters of them. We're pouring out milliliters, and since the molarity symbols here cancel out and I'm left with these units, I'm just going to leave it as milliliters. I think that's probably the easier way to go when you're trying to work those out. Okay, so hopefully you got that one. And again, there'll be some practice of these types of problems for you in that packet. That's, if you go to the KCS website under Student Resources, you'll be able to see those. All right, so we're going to switch gears here a little bit. We're going to talk about something different here. We're going to talk about acids and bases. Again, acids and bases are probably something that you've talked about since elementary school. You probably talked about pHs, and you probably talked about litmus paper and all of those sorts of things. We're just going to do a real quick overview so that those of you all that are going to be going on to more chem classes next year will have a little bit of a clue about acids and bases and be able to do some really simple calculations with them. So remember, acids are things that produce H+. So if we had a hydrochloric acid and we broke that apart, we put that into water, okay, it would break apart into H+ and Cl-. So we would have chloride ions and we would have H+ ions. Those H+ ions are what make it an acid. And technically speaking, what really forms is because those react with water, we get H3O+ ions, which are called hydronium ions. Really though, H+ and H3O+ are pretty much interchangeable for all the purposes that we're going to use them for. Now, if you did this in elementary or middle school, you probably learned that bases were things that produce OH. For us in high school, that is true. If something produces OH, it is a base. But it's actually a little bit more complicated scenario. A base is going to be something that is going to accept a proton to itself. In other words, it can absorb an H+. An example of that would be something like ammonia. Okay, if we could put ammonia into water, and what would happen is that the water is going to give off one of its hydrogens to the NH3, and we're going to get an ammonium ion, and we're also going to get an OH. So technically, yes, an OH was produced, but the OH wasn't produced out of the ammonia. Instead, the ammonia absorbed or accepted an H+ ion to become the ammonium ion that you probably remember from your polyatomic ions. Okay, so that's the definitions of them. Really, technically speaking, that would be what we call the Bronsted-Lowry definitions for acids and bases. We're not going to get into all the theories for all those, but you can certainly look up some videos that are going to talk about Arrhenius and Bronsted-Lowry and Lewis acids and bases. The Bronsted-Lowry system here will get you through everything you need to know in high school Chem 1, though. So let's talk real quick a little bit about the math behind this and about your good friend, the pH scale. I'm sure that each and every one of you look at the pH scale in elementary school. And it's just a simplified way to sort of give us a quick estimate of is something basic or alkaline, okay, you see that term here, or is it acidic? And it's real easy for us, assuming that we're normal room temperature, neutral pH is 7, okay, so that's neutral. Anything below that is an acid, and anything above that we could say is a base. Okay, or we could say that it was basic or that it was acidic. Now again, those are sort of, I mean, that's a number value, so that's a quantitative value, but what you probably didn't talk about in elementary or middle school is how you actually calculate that. And the reason that you didn't talk about that is because of the formula here. And this is the formula for calculating pH. And you see that, first off, you see this, what is a log? Well, we'll talk about that in just a second. I'm not going to teach you guys about logarithms. But logarithms and exponential notation is just sort of a way to take care of really small numbers or really big numbers and make them a little bit more comprehensible. So talking about something having a pH of 1 makes a lot more sense to us than talking about the fact that maybe, hey, we've got this acidic substance that it has a hydronium ion concentration of 1.6 times 10 to the -8th. Okay, so giving a pH value is a much more sort of accessible way to grab onto that number. But in reality, we want to know, or we want to be able to turn those things into the concentrations that we use in chemistry as well. So how does that work? Well, when you see these brackets here, okay, brackets typically mean molarity. And of course, we've just talked about molarity. Molarity is moles per liter. Sorry for that terrible handwriting there. Molarity is in moles per liter. And so if we know how many moles of H+ are in a liter of solution, we could then plug that in and be able to find the pH. Now you might be asking yourself, what do I mean by plug that in? Well, if you grab your good friend the calculator, you'll notice that there is a log key right there. Okay, log key is the logarithm key. Technically speaking, that means the log base 10 key, but we're not going to get into all that. That log key is everything that you need to be able to solve for pH right now. So if I've got a 0.025 molar solution of nitric acid, that's what HNO3 is, then what is its pH? Well, first off, to be really technical, we would have to say that HNO3 is a strong acid, and that strong acid is going to break up into H plus and nitrate. Now, I don't really care about the nitrate. That doesn't really mean anything to me, but I do care a lot about that H plus because that's how I get to pH. Now, since it's a strong acid, that all breaks apart, and so that means that my H plus concentration is the concentration of the acid overall. Now, is that always the case? No, it's only true for strong acids. But if you want to talk about how that works for weak acids, sign up to take AP Chem, and your AP Chem teacher will teach you about equilibrium and acid dissociation constants and all that fun stuff. For us, all that matters is that if it's a strong acid, the concentration that we're given is the H plus concentration. So that gives us something that we know automatically at the beginning. We know that our H plus concentration is 0.025. And so then we're going to take our equation and we're going to plug this stuff in. Okay? So of my H plus concentration, I wrote all that out just to say that the negative log of 0.025 is what I'm going to plug into my calculator. Now here's what's really important. On your calculator, you should have a negative key that is not the minus key. So use that negative key, hit that, then hit your log button, okay, and then plug in 0.025. And when you plug that in, you should get, and let me check my notes here real quick, you should get 1.6. You're actually going to get a little bit more in your calculator, obviously, than 1.6. But since this had 2 sig figs in it, I'm going to give 2 sig figs to my answer. And so that is the pH of that solution. You would want to stop real quick and make sure that that answer makes sense. Nitric acid is a strong acid. While that doesn't seem like a super high concentration, it is fairly a high concentration, and so it's going to have a really low pH. It's a strong acid solution. Really low pH makes really good sense. So what would you do if you needed the H plus concentration and you were given the pH? Well, this is a slightly more complicated way to do this, or a slightly more complicated problem to figure out. I'm going to run you through one real quick, but here's what I would tell you. If you can't do these yet, I wouldn't stress too hard about that. If you're working out the problems on the activity sheet and you want to shoot me an email because you don't understand something, you can certainly do that. But here's our equation. I'm going to go ahead and plug in the pH. I know the pH is 3.5. And so this is what I'm left with. I'm looking for my H plus. This is my X value. The problem is, of course, since we haven't done logarithms yet, because most of you all are not in Algebra 2 or Integrated Math 2 or 3, you might not know what to do with that. So I'm going to make it real easy for you. On your calculator, if you look over here on your good friend the calculator, and it's okay if you're not using the same type of calculator I am, look for the 10x key. You should have a key on your calculator somewhere that says 10 to the x power. That's the key you want to use here. I'm going to show you algebraically how that works. I'm going to algebraically essentially divide or multiply both sides by -1. That's going to get rid of this negative and make it positive. It's going to move the negative over here. Okay? That's going to leave us with this. And then to get rid of the log, algebraically, I'm going to use my 10x key. In other words, we would say in math terms, I would take the base 10 of each side. You don't need to worry about the theory behind that. All you need to know is that 10x key on your calculator is going to cancel out this log, and we're going to get this. 10 to the -3.5 is equal to my H plus concentration. On your calculator, if you're using the calculator I am, you would hit the second key and then the log key, and it would actually tell you 10, and then it would say parentheses. You would put in -3.5. Again, use the little negative key right there, okay? And then plug that in, and then you would get a number out, and the number that my calculator spit out for me, let me grab my notes here real quick, was 3.2 times 10 to the -4th, and that's going to be moles per liter, or molar is my H plus concentration. Now, of course, your calculator probably didn't kick that out. Your calculator probably kicked out 0.0003, I don't know, it might have been 1/6 or something if I remember correctly. And then we're going to round that, of course, to our proper number of sig figs. Again, don't let the sig fig part of that stress you out. I would say that if you're not comfortable with this part, don't stress about that. If you can do the previous problems, then you're in pretty good shape for most of high school Chemistry 1. So I wouldn't stress too hard about that. Now, just as a little added bonus for you guys, I want to talk to you about something called titrations. Titrations are essentially a lab that we would do to determine the unknown concentration of something. So the way that that would work in a lab setting is that your teacher would probably give you, have a bunch of unknowns up there and would give each lab group a sample of that and say, hey, this is hydrochloric acid, but I want you to tell me what the concentration is. This is a real practical, real world thing. I used to work in an industrial chemical plant, and one of the things that I had to do all the time was to determine the concentration of things before we shipped them out. And so the way that I would do that is I would do a titration. Now, titration is going to involve you measuring with a burette. A burette, remember, is one of your pieces of lab equipment that can accurately measure volume. So in that burette, you would have, in many cases, you would have a base if you were measuring the concentration of the unknown concentration of an acid. And then you would slowly add that in until you got a color change. And you'll notice that the color in this flask is a really light pink. That is the color that something called phenolphthalein turns when you neutralize the acid in it. You're looking for this really pale pink color. So I'm done talking in the video, but I'm going to show you a little clip here of me doing a titration so that you can actually see how this works, because I know a lot of you guys had to miss out on actually doing a titration lab, and that's probably the most fun lab of the year. Hopefully you'll take another science class and get a chance to do that titration. Okay? Thanks a lot. I hope you guys enjoyed this lesson on concentrations and a little bit of acids and bases.